Hello again, this is Professor Roman. Let's continue the lecture series, Transition to Advanced Mathematics. We are discussing combinatorics at the moment, the art of counting. Now let's consider another problem where we have to muster all of our skills at logical thinking and much of what we've learned about binomial coefficients. There may be shorter solutions to this problem than the one I'm going to give you, but the following solution does show a typical thought process behind problem solving, in particular in this kind of setting. So the question is, how many ways can a set S of size n be partitioned into two indistinguishable and possibly empty subsets, x and y, that are disjoint and whose union is S? So x and y are disjoint and their union is S. So what I could have written, and I didn't, was x is the disjoint union of x and y. How many ways can you do that? But we're not distinguishing between the set on the left and the set on the right. So it doesn't matter. They're indistinguishable sets for this purpose. Now, well, the union, of course, x union y is all of S, which means y is actually the complement of x relative to S. So pretend our S is our universe, so we can just use the term complement. So such a partition can be denoted this way, x bar x complement, where x is a subset of S. And the issue is to count the number of such partitions. But we have to be careful because we're not distinguishing between the two subsets in the partition, and so x bar x complement and x complement bar x are the same partition. I should mention maybe in passing that the term partition is a technical term in mathematics, and we're going to study partitions later on, but in that sense, in the technical sense, the subsets in a partition are not allowed to be empty. But here we are allowing them to be empty. So the term partition here is being used informally and not in the strict formal mathematical sense of the word. Okay. Now, one argument you could advance is the following. Let's simply list all possible subsets of S on the left of a bar and place the complements on the right side of the bar, and we get a list of that looks like this: x1, x1 complement, x2, x2 complement, all the way down to, since there are 2 to the n such subsets, x sub 2 to the n along with its complement. Then we notice that there are duplicates in this list because any set and its complement could be reversed, write the complement to the left side of the bar, and these are in fact the same partition because, again, the subsets are indistinguishable for our purposes. And there are, these range from, I could be a 1, excuse me, that should be a 1, I better fix that. 1 to 2 to the n. And since they're split up in pairs, you would argue that the length of this list is half of 2 to the n, or 2 to the n minus 1. So there are 2 to the n minus 1 partitions. This is correct. There are 2 to the n minus 1 partitions. But this argument is lacking. It really needs further justification. How do we know, for example, that there are no other duplicate entries in the list? How do we know that all the partitions are accounted for in the list? There's some incompleteness here that someone with a very detailed mind would say, I'm just not happy with this. I need to be convinced further. So let's take a bit more careful approach to how we construct the list. One way to gain more control over the list is to use the sizes of the subsets involved. Placing the smaller subsets on the left of the bar and their larger complements on the right. And in this way we can avoid introducing any duplicates at all right from the beginning. Now, I should add here, maybe I should have said this a little earlier, we are thinking out loud right now. We proposed a certain argument, we wrote it down, we decided that maybe it's not quite good enough, so we're still thinking about how to approach this problem. But I wanted to include everything in this solution so you would see it all laid out. At the end, I'm going to say, well, a lot of this stuff at the beginning could be left out. It was basically could be done on scratch paper until you get to the point where you see exactly what to do. Then you can write a polished, finished proof for publication or for other people to view. But for now, we're going through everything, the thought process as well as the finished product. Now, oftentimes, the best way to get a clearer picture of how to proceed is to try some small examples. We have an idea here that we're going to put the smaller sets on the left and the bigger sets, their complements, on the right. Let's take a look at a couple of instances of that. And one thing you will discover through experience, and you don't need that experience because I'm about to tell you, is that oftentimes parity plays a role in these things. If a set has odd size, the argument may go a little differently than if the set has even size. So when we try a couple of small examples, we'll pick a set of odd size and a set of even size. So we'll start with this small set, s equals 1, 2, 3, which of course is odd. Then we start listing on the left the small sets. Set of size 0, sets of size 1. And we put their complements on the other side. Now the next step would be to put a set of size 2 on the left, but we get to stop because those are already on the right. We don't need any additional set. We can't, in fact, add any additional lines to this list. We have all the sets of size 0 and 1 on the left, and all the sets of size 2 and 3 are on the right. So we write down carefully our observations. By construction, the subsets on the left side of the bars are distinct because we did it that way. We built this list on the left. And they account for all subsets of S of size at most 1. Well, it follows then that the subsets on the right side are all distinct. And if you need a little bit more explanation on that, just look at this biconditional. Two sets, x complement equals y complement if and only if x equals y. So that's the reason. If this set's distinct, then if this list on the left is distinct, the list on the right is also distinct. Moreover, the subsets on the right account for all subsets that have size at least 3. Oops, at least 2. Here it is in symbols. If the size of x, which I'll call I, is less than or equal to 1, so it's on the left side, then the size of X complement is equal to 3 minus I, which is bigger than or equal to 2. So all these sets have size at least 2. But this is a biconditional. It goes the other way. So if any set has size at least 2, its complement has size at most 1, and so is on the left. Therefore, the first set I mentioned is on the right. So the list includes all of the subsets of S. Small ones on the left, big ones on the right. In particular, size less than or equal to 1 on the left, size bigger than or equal to 2 on the right. Okay. So since every subset of S is included, and included exactly once, we have a complete list of the possible partitions with no duplicates. If you said, why is that? I would say, well, if you don't think that's a complete list, you're going to have to come up with another partition, which means you're going to have to come up with another subset of S, that is part of that partition, but it's already on my list, opposite its complement. So this is a complete list, and this is the justification. Now, I don't know, maybe this will seem a little pedantic to you, a little too detailed, but the point here is that this is complete. It's a complete explanation. There should be no room for questions. How do you know this? How do you know that? How do you know it's complete? How do you know there's no duplicates? It's all answered here. And that is, after all, what we're looking for in a proof. No gaps. Little tiny gaps are okay, and you have to use your judgment on what that means. And again, as we've discussed, I think, before, it depends on your audience. Right? In a research paper, you can have big gaps, hopefully not too big, because you want to make sure that they can be filled in correctly. In a lower level textbook, you would have fewer gaps. But we also mentioned the fact that having absolutely no gaps isn't necessarily kind to the reader. So I'm thinking about this from the perspective that you're writing it for me to look at. And that's when I don't like to see gaps. If it was the other way around, and I was writing this for you, and I wasn't teaching you how to do proof techniques, I was just writing, this was just a book on combinatorics, a first book on combinatorics, I would leave a few little gaps to help you get practice thinking about how to proceed. Okay. So these are subtleties which I'm sure you haven't thought about before, and I dare say most courses in transition courses are not going to go into it in this detail, but I think it's good for you to hear this conversation. Now, we need to look at one more case, and that's because we want to see what happens if the set S has even size. So we'll go with the set 1, 2, 3, 4. It might work with the set 1, 2, but that's a little small, and I'm afraid that we might lose some of the ideas we need if we look at too small a case. So hopefully this analysis will go in a manner quite similar to the one we just did. But we have to expect that because we've changed parity from odd to even, there may be some other issues that come up. Maybe not, but there may be. Well, we can start, as in the previous case, we can still list the sets of size at most 1, the small sets on the left, and their complements on the right. But now, as we got this far, we realize we still have sets of size 2 that must be added to this list. We can't dump them all on the left because their complements also have size 2, and we will be in some trouble. We have to split them in half. Half of them on the left and half of them on the right. or put it better, half of them on the left and their complements on the right. So we don't want a set and its complement on the left. Well, one way we can handle this, dealing here with the doubleton sets, that means sets of size 2, is to pick an element from the set S, and I'll pick 1, and list all the doubleton subsets that contain 1 on the left. And their complements will go on the right, and of course none of those contain 1. And you should know now, and you can do this computation if you need to, that among all the subsets of size 2, half of them will contain 1 and half won't contain 1. Now so we add these to the list, and now we can make the following observations. The subsets on the left side of the bars are distinct, again by construction, and account for all of the subsets of S that have size at most 1, as well as half the subsets of S that have size equal to 2. 2 is the balancing point, because n is even now, n over 2 is an integer. That is sort of our critical point here. So it follows that the subsets on the right side of the bars are distinct, same reason as before, and account for all the subsets of S that have size at least 4 minus 1, which is 3, so that's this group here, as well as half the subsets of S that have size 2. Those will be the ones that don't contain the integer 1. So all the subsets of size 2 appear on the list on one side or another. So by size, we have all the subsets of S. The small ones, less than or equal to 1, are on the left. The big ones, greater than or equal to 3, are on the right. Then the ones that have size 2, which is the only size left, are split evenly on both sides. So, again, every set appears exactly once in this list. It must be a complete list of all the partitions. We now have an analysis in 2 cases, and we can now attempt to generalize. Once we get the list, hopefully we can count its size, and that'll answer the original question. The original question wasn't to create a list. Maybe it should have been, or could have been, so we'd actually need to see these lists. But I just simply wrote the question, how many are there? Okay. So here's how we generalize. If the size of the set S is odd, say at n equals 2k plus 1, then we list every subset x of S of size at most k. See, k is now 1. K was 1 in our first example, n equals 3. So at most k on the left, matching with the complements on the right. And we can say the following. By construction, the subsets on the left side of the bars are distinct and account for all subsets of S of size at most k. We did that deliberately. It follows that the subsets on the right side of the bars are also distinct. Again, the reasoning is this. And also, these subsets account for all subsets that have size at least n minus k, which is k plus 1, because of this biconditional. It looks just like the one we did in the small case where we replace 1 by k. So for the same reason, we've got every subset in the list exactly once we have a complete list of all the possible partitions of S into the two disjoint subsets. No duplicates. This is an immediate generalization of the first case. All we did was change 1 to K. It went very smoothly. It doesn't always work quite that way. I think most of the time you'll do a couple of small cases, and when you turn to generalizing, you'll discover more problems that you didn't realize because they didn't exist in the first couple of small cases. But in this case, it went very smoothly. We were able to generalize the odd cases very easily. How about the even cases? Suppose that the size of S is even, say n equals 2K. Then we're going to, following the same procedure basically, until we get to the halfway point, which is size K, we'll list every subset X of S of size at most K minus 1 on the left, matching it with its complement on the right. Then, modeling what we did before, was select any given element, little s, from capital S, and list all of the subsets of size n over 2, namely K, that contain S on the left, matching them with their complements on the right. And those complements do not contain S. So we can reason the same way we reasoned before. The subsets on the left side of the bars are distinct and account for all of the subsets of S that have size at most K minus 1, as well as half the subsets of S that have size equal to K. The subsets on the right side of the bars are distinct, because the ones on the left side are, and account for all the subsets of S that have size at least n minus K minus 1, which is at least K plus 1, as well as half the subsets of size K. So all subsets of S of size different from K, less than or equal to K minus 1, greater than or equal to K plus 1, appear exactly once on the list. And the subsets of size K also appear exactly once on the list. And there's no duplicates across the bars because all the subsets of size K on the left contain little s, but none of them on the right contain little s. So again, we have a complete list because every subset of S appears somewhere on the list with no duplicates. Well now, when we examine the list, any one of these lists, this is one that's written out, obviously we've got all the sets included, 2 to the n sets, but they're matched in pairs. Doesn't even matter whether they're complement pairs, they're just matched up in distinct pairs. So the length of the list is half of 2 to the n. And that is a complete, carefully thought out proof. And as I said before, this is what I've written here is quite long, relatively speaking, but you can start the official proof here. If the size of S is odd, we do so-and-so. Otherwise, if it's even, we do so-and-so. Now, you would preface this with a sentence. You would say something. You would still probably want to include the very beginning of this, which goes way back here. You'd still want to say, well, the partitions look like this, X and X complement. And the issue is to count these partitions. And these two are the same because the sets are indistinguishable. And then you might say, for our proof, we'll consider two cases. S of even size and s of odd size. And then you can, you can jump all the way down to here. So you can skip this entire page of special cases and just start in right here. And so your proof now is going to be much shorter. It's going to be from here. That's a little hard to get all this in the camera, but it's going to be about a page rather than 2.5 pages almost. Okay. Binomial coefficients are often arranged in a triangle known as Pascal's triangle, and here's how the triangle begins. The nth row of this triangle, and n starts at 0, contains the n plus 1 binomial coefficients whose upper number is n. So this is what the nth row looks like. N goes in the upper number, and the lower number ranges from 0 to n, which is why there are n plus 1 of them. Actually, these are the coefficients in the binomial expansion of x plus y to the n, so that's another way to remember what goes in a given row. This is a typical piece of Pascal's triangle. And some of the properties of the binomial coefficients can be expressed nicely using the triangle. For example, Pascal's formula, which as you know is this, can be read off of this triangle. If you want to add two consecutive entries in a given row, their sum is the entry in the next row below those two entries. Okay. If you look at the first, this is the reason I really wanted to bring up Pascal's triangle, is if you look at these rows here and you look at the sizes of the numbers, you'll see a pattern. If you start with the third row, which is n equals 2, you'll see that there's an increase and then a decrease. Here, in the next row, increase, constant, decrease. Increase, increase, decrease, decrease. Increase, increase, constant, decrease, decrease, and so on. Well, sometimes there's a double peak or a double maximum, 3 here, 10 here. Other times there's a single maximum for the coefficients in that row. And it depends on whether the row is, the n here is indexed by an even number or an odd number. So what it appears from the first portion of the triangle, and this is not a proof, is that when n is even, then there's an odd number of binomial coefficients. They're going to look like this. Their relationship. They're going to start to increase until they hit the middle. N choose n over 2. Since n is even, this is an integer. Then they're going to decrease. Single peak or single maximum is a better way to say it. When n is odd, these two values by mirror symmetry are the same. So there's a double maximum. All the other binomial coefficients are smaller. They increase till they hit this double maximum, then they decrease. Note also that I talked about the greatest integer function once before. The greatest integer in R. The greatest integer in n over 2 will be n over 2 when n is even, and it'll be n minus 1 quantity over 2 when n is odd. So we get a formula that looks like this. the binomial coefficient n choose 2 is less than or equal to n choose greatest integer in n over 2. Most of the time this is a strict inequality. It's the only time it's an equal sign is when k equals n over 2 in the even case, then these lower numbers are identical, or when k is n plus or minus 1 over 2 when n is odd. So in loose terms, there are more subsets of a set of size n that have middle size, either exactly the middle when n is even or on either side of the exact middle when n is odd. So for example, there are more subsets of a set of size 10 that have size 5 than there are any other size. You can remember that easily because n choose 0 is 1 and n choose n is 1, so the outside numbers are as small as they can be, and they grow from both directions until they come into the center. This is very important in combinatorics, and so we give a formal theorem here with a formal proof. Let n be a positive integer. If n is even, then the largest value of n choose k, the binomial coefficient, occurs exactly once. N choose n over 2, half size subsets. If n is odd, then the largest value occurs exactly twice at these 2 points. And we have this general inequality, which oftentimes is all you need, but is really missing quite a lot of information because this inequality is almost always strict, as we said. As for proof, one way is to consider the ratio of two consecutive binomial coefficients. I put n choose k in the numerator, n choose k minus 1 in the denominator. Write it out in terms of factorials. It cleans up quite a lot. So we can now observe that n choose k minus 1 is strictly less than n choose k if and only if rk, this ratio, is bigger than 1. This one goes on the top, this goes on the bottom. And that holds if and only if k is less than the quantity n plus 1 over 2, which you get by using this expression here. The two binomial coefficients are equal if and only if rk is 1, if and only if k is equal to this value. And the binomial coefficients begin to descend because the lower number here is bigger. K is bigger than k minus 1, but this is an inequality here. If and only if rk is less than 1, if and only if k is greater than n plus 1 over 2. So now if n is odd, then n plus 1 over 2 is an integer. So these are all integers. And this tells us that the binomial coefficients increase until you hit this n choose k minus 1, which is equal to n choose k, for this k. For this specific k is when the binomial coefficients reach their peak. And these two are equal, so we peak out right here. If k is equal to this, k minus 1 is equal to n minus 1 over 2. When n is even, n plus 1 over 2, which is n over 2 plus a half, is not an integer. So to say that an integer is less than this would be the same as saying it's less than n over 2. And so we can sharpen this previous display here, and it looks like this. Pretty much everything's the same except the third column. K is less than n over 2. This can never happen because k can never equal a non-integer. and then k is greater than n over 2 plus 1. So this tells us that the peak comes at n choose n over 2. This one can never happen, and then so we have an immediate descent. So we've got a single peak here, a single maximum at n choose n over 2.